In this video, we will add another tool to our toolbox for evaluating integrals using the method of partial fractions. So a quick recap of partial fractions. uh, if you have distinct linear factors, then we can set up partial fractions using a over one of the linear factors plus b over another linear factor. If you have repeated linear factors, then you would set up as a over first linear factor plus b over x plus 1 plus c over x plus 1 squared. If we have distinct quadratic factors, actually this is not distinct quadratic, this one is distinct quadratic and linear factors in here. So the linear factor gets a over x minus 5, quadratic factor gives bx plus c over 2x squared plus 1. If we have improper fractions, then start with the long division first. Okay, let's look at some examples for integrating using partial fractions. So here's another review what partial fractions are. In the past, in intermediate algebra, we saw how to add these two fractions and get to the sum. The method of partial fraction actually breaks this sum back into the two fractions it started with. As you can see, integrating that sum is a bit harder, or sometimes it's not even possible. Integrating the two separate fractions that actually came added to that sum or subtracted to that sum is a lot easier. So this second integrand is called the partial fraction decomposition of the first integrand. Okay, so we will start with the examples. Let's see. 1 over x squared plus x minus 1. First of all, I'm going to focus on doing the partial fractions for 1 over x squared plus x minus 2. Let's go ahead and factor 1 over x squared plus x minus 2. So we are trying to come up with the two fractions that were added or subtracted to give us this sum. Okay. So we have x plus 2 and x minus 1. X plus 2, x minus 1. Now let's set up the partial fractions for this one. Both are distinct linear factors. So we have a over x plus 2 plus b over x minus 1. A over x plus 2 plus b over x minus 1. Okay, multiply both sides. Multiply both sides with x plus 2 and x minus 1. It's going to leave us with 1 equals a times x minus 1 plus b times x plus 2. Now at this point, we can distribute a inside the parentheses, b inside the parentheses, and then equate the coefficients of x and then x squared and the constant terms, or we can use clever substitution. So I'm going to let x be equal to 1. The benefit of doing that is this factor will turn into 0, and I would be able to find out my b. It turns out to be b equals 1 plus 2, which is 1 plus 2. 1 is equal to 3b. B comes out to be 1/3. And now I can let x be negative 2. The benefit of that is this factor will turn into 0 and I can find out my a. The left hand side has no x, so it doesn't care for the x. 1 equals a times negative 2 minus 1. So 1 is equal to negative 3a. A comes out to be negative 1/3. All right, so we can break our fraction into, we can plug the a back at the spot of a and the b back where it belongs. The a is negative 1/3 x plus 2 minus plus 1/3. Don't mix a and b. If a was on the top of x plus 2, then keep a on the top of x plus 2. And the b is positive 1/3, and b has x minus 1 dx. We can integrate these two pieces individually. Negative 1/3, 1, positive 1/3, 1 over x minus 1 dx. So it's negative 1/3. Integral of 1 over x plus 2 is natural log of x plus 2. We have the derivative of this sitting on the top. So you can do u substitution, or you can directly see that's going to be the natural log of x plus 2 and natural log of x minus 1. And that's the method of partial fractions. We just went ahead and evaluated this integral using the method of partial fractions. Okay, let's check out another example. Partial fractions where we have three distinct linear factors. So first of all, I'm going to do the work for method of partial, or just do the partial fraction decomposition over there on the top of the problem. Let's go ahead and factor the denominator. If I factor, I'm left with x squared minus 1, which is 3x squared minus 7x minus 2 over x times x plus 1 times x minus 1. Okay. And now when I set up, I have three distinct linear factors. So I can say a over x plus b over x plus 1 plus c over x minus 1. We can set up three distinct linear factors here. Three different fractions because we have three distinct linear factors. Now, back to the problem. So I'm going to multiply both sides, everything on both sides, with x times x plus 1 times x minus 1. Okay, so go ahead and distribute the whole thing in there. So we would have 3x squared minus 7x minus 2 equals a. The x and x will cancel. We would have x plus 1, x minus 1, plus b. We would have x times x minus 1 plus c, x times x plus 1. All right. Now, we can distribute, combine all the like terms, and then equate the coefficients of x squared and x and the constant term. But I think it's a little bit easier here to substitute, do the clever substitution. Okay, clever substitution, I'm going to let x be 0. If I let x be 0, both b and c will turn into 0 because they have a factor of x in there, and I would be able to find out the a. So if x is 0, my left-hand side is negative 2. The right-hand side comes out to be 1 times negative 1. So I can say a is equal to 2 if I do clever substitution, x equal to 0. Next, I'm going to let x be positive 1. If x is positive 1, all the factors that contain x minus 1 are going to turn into 0, and I will be able to find out the factor or the constant c here. So if x is positive 1, the left-hand side is 3 minus 7 minus 2. The right-hand side is c times 1 times 2. Okay. 3 minus 7, that's 3 minus 9, that's negative 6, equals 2c. So I can say c is negative 3. C is negative 3. Okay, now let's go ahead and find, now I'm going to do the clever substitution, let x be negative 1. If I let x be negative 1, then all the factors that contain x plus 1 will turn into 0, and I will be able to find out the b. If I let x be negative 1 on both sides, let's see, what does it turn out to be? 3 times negative 1 squared is just 3. If I plug -1 for x plus 7 minus 2 equal to c times -1 times -1. No, we won't be able to. We already found the c, so that's not correct. C will actually turn into 0. So I'm going to be left with B in this case when I call x as -1. Okay. 3 plus 7 is 10. 10 minus 2 is 8. B times -1 times -2. 8 is equal to 2b. B comes out to be 4. We are ready to break our integral into partial fractions. So plug the a back for whatever. Plug a, b, and c back in here. And we would get a was 2, so 2 over x. I'm also going to separate the integral. B was 4 over x plus 1 dx minus c was -3, that's why I'm writing minus, and I can pull the 3 out, 1 over x minus 1 dx. So performing the integration, 2 natural log of x plus 4 natural log of x plus 1 minus 3 natural log of x minus 1 plus ac. Okay, that's all we are left with. Let's check out our next example. Partial fraction when we have to do long division. So let's check out when we have to do long division. Here you have a top heavy polynomial. On the homework, it would not tell you to do long division, but you have to recognize if you have a top heavy polynomial, the top numerator degree is higher than the denominator degree, then you have to do long division first. So 2x to the third, let me write a little bit smaller, dividing with x squared minus 2x minus 8, 2x to the third minus 4x squared minus 15x plus 5. Okay, so let's see. X squared times what gives me 2x to the third? It would be 2x. It's 2x to the third minus 4x squared minus 16x. So subtraction, addition, and addition. So that leaves us with x plus 5. So that means we can write this fraction as 2x plus x plus 5 divided by x squared minus 2x minus 8. So I'm going to be doing the partial fractions for this portion now. So partial fraction decomposition. Let's see, we can do x plus 5 over x squared minus 2x minus 8. If I break it, it turns out to be x plus 5. Factor the numerator. That turns out to be x minus 4. And then x plus 2. Let us set up the partial fractions. X minus 4, x plus 2 equals a over x minus 4 plus b over x plus 2. Multiply both sides with x minus 4, x plus 2. Left hand side is x plus 5. The right hand side turns out to be a times x plus 2, b times x minus 4. Okay, so we're going to let x be -2. Then I can find out the b. So -2 plus 3, -2 plus 5 is 3. And -2 minus 4 is -6. So I can say b is 3 over -6 or -1/2. Now I'm going to let x be positive 4. So that turns out to be 9 is equal to 6a. A comes out to be 9 over 6, which is 3/2. Okay, so we have broken our fraction into the pieces. So this is 2x plus x plus 5 over x squared minus 2x minus 8 dx. Now further, we did do the partial fraction for this piece, and the partial fractions are equal to a, so plug the a and b into the highlighted expression. A was 3 halves, so plus 3 halves x minus 4, and b was negative 1 halves x plus 2. Okay, the whole thing dx. All right, so now we got 2x dx plus 3 halves 1 over x minus 4 dx minus 1 half 1 over x plus 2 dx. We can go ahead and integrate the pieces. So it turns out to be 2x squared over 2 plus 3 half natural log of x minus 4 minus 1 half natural log of x plus 2. Again, you can do the u substitution. Derivative of bottom is sitting on the top. You can call the u as x minus 4 and du will be on the top. Same thing for 1 over x plus 2. You can call x plus 2 as u and go from there. Next example. Let's go ahead and factor the denominator and see how does the denominator look. Okay, x to the third, so I can pull out an x, and inside would be x squared plus 2x plus 1 dx, which is 5x squared plus 20x plus 6 over x times x plus 1 squared dx. So now I have repeated linear factors. So I'm going to first do some work on the partial fractions, and then we will come back to the integral. 5x squared plus 20x plus 6 over x times x plus 1 squared. We set up the partial fractions as a over x, b over x plus 1, c over x plus 1 squared. We're going to multiply the whole equation with x times x plus 1 squared. The left-hand side would be 5x squared plus 20x plus 6. The denominator will cancel. The right-hand side would be a times x plus 1 squared plus b times x plus 1 plus c times x. Okay, so to evaluate this integral, let's see. We can open up, FOIL the x plus 1 squared, distribute, combine the like terms, and then equate the coefficients. We can do that. Or let's go ahead and find the x. Let's go ahead and let x be 0 first. Let x be 0. If I let x be 0, I will have all the factors that have x as 0 in there. All the factors that have x in there will be gone. They will turn into 0. So if I let x be 0 on both sides, I am left with 6 equal to a times 1. So a turns out to be, nope, not a times 1. Sorry about that. Yeah, it is a times 1. So a comes out to be 6, right? A comes out to be 6, positive 6. Okay, that is not a negative sign. It comes out to be positive 6. Okay, so now we can let x be negative 1. If I let x be negative 1, then all the factors, I would be able to find the c in there. So let's go ahead and let the x be negative 1 on both sides. So I would have 5 times negative 1 squared, which is just 1, plus 20 times negative 1 plus 6 equals c times negative 1. So it's 5 minus 20, which is negative 15. Negative 15 plus 6 is negative 9. Negative 9 is equal to negative c, gives c equals positive 9. So I found the a and the c, but there's no other clever substitution or no other number I can plug in to make the factors a and c 0 and keep the b. So I'm just going to go ahead and plug x equal to any number, any easy number. I'm going to plug x as 1 on both sides. Since I know a and c now, it should be easier for me to find the b. If I plug x as 1, I have 5 plus 20 plus 6 equals a times 1 plus 1 is 2 squared plus b times 2 plus c. So that's 20 plus 5 is 25 plus 6 is 31 is equal to 4a plus 2b plus c. Let us replace the a by 6 and c by 9. So 31 equals 24 plus 9 plus 2b. What is 24 plus 9? It is 33. 31 minus 33 is 2b. That's negative 2 is 2b. We get b as negative 1. So we have found our a, b, and c. We are ready to break our integral into the pieces. Okay, so I'm going to break our integral into pieces. So I'm going to write it in terms of partial fractions, plug the a, b, and c back where they belong. A over x, which is going to be 6 over x, plus b over x plus 1, negative 1 over x plus 1, plus c over x plus 1 squared, and c is 9 over x plus 1 squared dx. So if I plug a, b, and c where they belong, we can split it into 3 different integrals. So it's 6 over x dx minus 1 over x plus 1 dx plus 9 over x plus 1 square dx. Okay, so I'm just going to call this integrand 1, 2, and 3. I'm going to do integrand 3 on the scratch work because this is a clear u substitution. So if I let u be x plus 1, du will be dx. So this is u to the power negative 2 du, which turns out to be u to the power negative 1. I'm not going to bother about plus c yet. We will take care of it with our final answer. So this third integrand actually turns out to be negative 1 over x plus 1. Okay, so I'm going to plug these back in there. So this is 6 natural log of x minus natural log of x plus 1. Notice I'm putting the absolute value bars because I'm not sure if these are positive or negative depending on what x is, and natural log always is positive, so that's why the absolute value bars. Plus, actually it would be negative now because I'm plugging in, it would be negative 9 or minus 9 over x plus 1 plus c. And that's what our integral turns out to be. Okay, let's see the next example. In this case, looks like I can factor the numerator. So let's go ahead and factor the numerators. But I also have a quadratic factor over here. This one is factorable. So 2x to the third minus 4x minus 8 divided by x times x minus 1 and then x squared plus 4. So when I set up the partial fractions, I'm going to call this number 1. We will come back to number 1 integrand. Right now I'm going to focus on the partial fractions. Okay, x times x minus 1 and then times x squared plus 4. This turns out to be, let us check, a over x plus b over x minus 1 plus cx plus d over x squared plus 4. Okay, now let's go ahead and multiply both sides with the entire denominator, x times x minus 1 times x squared plus 4. Why are we using cx plus d? Because we have a quadratic factor. Okay. Left hand side turned out to be 2x cubed minus 4x minus 8. 8 times x minus 1, x squared plus 4, plus b times x squared plus 4, plus c times x minus 1. So again, I'm going to try the clever substitution. Let x be 0. If I let x be 0 on both the sides, and I have negative 8 on the left hand side, and both b and c will actually turn into 0. I'm only going to be left with a times negative 1 times 4. This gives me negative 8 is equal to negative 4a. A is equal to 2. A turns out to be 2. Okay, now I'm going to let x be positive 1. The benefit of that, all the factors that contain a 1, x minus 1 factor in there will turn into 0. So if x is positive 1, I have 2 minus 4 minus 8. A and c will both go to 0, but we will have b left over. 1 squared plus 4 is 5. So 2 minus 4 is negative 2. Negative 2 minus 8 is negative 10 equals 5b. B comes out to be negative 2. So we found the b, we found the a. Now there's no other number that I can plug in that will make x squared plus 4 equal to 0. So I don't have any way to find out the c. Let's go ahead and try plugging in. May have to equate the coefficients. If I will have bx squared plus, let's see. So what I'm going to do really quick is I'm going to try to plug in any number here. Let's see. So let's plug in any number for x on both sides. So let x be 2 or something. Okay. So if I let x be 2 on both sides, so I would have 2 times 8, 2 to the third power, minus 4 times 2 minus 8 on the left hand side, and the right hand side would be 2 minus 1 is 1, 2 square is 4 plus 4 is 8, plus b times 2, 2 square is 4 plus 4 is 8, plus c times 2 minus 1 is 1. Let us clean up a little. 16 minus 8 minus 8. So that is 16 minus 8 minus 8, which is 8a plus 16b plus 2c. Okay, 8a plus 16b plus 2c. 16 minus 8 is actually 0. So 8 times a, what is a? Let's plug it back in. We know what a is. We also know what c is. No, we know what b is. Good. We'll be able to find out c in this case. So let's plug the b, whatever we found. 16 times negative 2 plus 2c. 8 times 2 is 16 minus 32 plus 2c. 16 minus 32 is negative 16 plus 2c. 16 is equal to 2c. C comes out to be 8 in this case. Oh. No. My bad. Okay, erase. I totally ignored this cx plus d over here. I only distributed to the c, but not to the d. Okay, my bad. Clean up. Clean up, please. Sorry. That I missed a factor there. Okay, so let's go back now. Right back to our setup was correct, but when I distributed, I missed the cx plus d. So we have 2x to the third minus 4x minus 8 is equal to a times x minus 1 times x squared plus 4 plus b times x squared plus 4 plus cx plus d times x times, excuse me, x squared x minus 1. Okay, so what I'm going to do here is I'm going to distribute FOIL and combine the like terms. So we have 2x to the third minus 4x minus 8 equals a times x to the third plus 4x, x to the third plus 4x minus x squared minus 4 plus b times x to the third plus 4x squared plus, this is, I'm going to think of this faster, is x squared minus x, right? So cx times x squared would be cx to the third minus cx squared plus dx squared minus dx. Okay, I'll write it. dx squared minus dx. If I combine, distribute a, and get all the terms together for a, b, and c, I get 2x to the third minus 4x minus 8. X cubed will have an a next to it, a plus b next to it, plus c next to it. And then x squared will have a negative a minus 4b, negative a minus 4b minus d next to it. And x will have, let's see, okay. X squared will have negative a bx squared, bx to the 4 x to the third plus 4x. Okay, minus a minus c plus d. I'm just combining the coefficients of x cubed, x squared, and x. And then we will have plus x, 4a plus 4b minus d. And then we have minus 4a as a constant. Now we can equate the coefficients of x cubed, coefficients of x squared, coefficients of x, and the coefficients of a. I think, but I'm also going to use a clever substitution like I did before. But if I equate the coefficients over here, I know the constant term on the right-hand side is 4a, and the constant term, so negative 4a has to equal negative 8, a has to equal 2. So we found our a. And if I do clever substitution in here, if I let x be 0, then I can easily find out if x is 0, then I can find out a. But if I let x be positive 1, so let's call this equation, let x be positive 1 in the highlighted equation. Let x be positive 1 in the highlighted equation on both the sides. I would have, this would give me 2 minus 4 minus 8. All the terms that contain x minus 1 will go to 0. We will be only left with 1 in here. So that's 2 minus 10. 2 minus 12 is negative 10 is equal to 5b. b comes out to be negative 2. Okay, so b is negative 2. This is going to help me finding the remaining terms. Now, if I equate the coefficients of x cubed on both sides, if I see x cubed has a plus b plus c next to it, it's got to equal to 2. So a plus b plus c has to equal to 2 if I equate the coefficients on both left and right hand side. Now I already found the a using comparing the constants. I already found the b using clever substitution. if you don't do this, you have to solve a lot of systems of equations if you equate the coefficients. So clever substitution did help me at least get some values. So A is positive 2, B is negative 2, and that turns out to be C is also equal to 2. Well, that's nice. C is also equal to 2. Let's go ahead and find the D now. So now I'm going to equate the coefficients of x squared. Do I have any x squared term on the left-hand side? No. That means the coefficient of x squared has to equal 0. Negative a minus c plus d has to equal to 0. Let's plug the a as negative 2, c plus d equal to 0. So this is going to give me d equal to 4. Okay, d is 4. All right, so set up the integral. Now isolate the fractions. A over x plus b over x minus 1 plus cx plus d over x squared plus 4. So we're left with a over x. Now I'm plugging these a, b, and c back into this fraction to set up our integral. Okay, so a over x plus b over x minus 1, b is negative 2, and then plus cx plus d, so that'd be 2x plus 4 over x squared plus 2. X squared plus 4, sorry. So that's what our integral is after partial fractions. So after partial fraction decomposition, we are left with this integral. Now let's go ahead and change it into the pieces. So 2 over x is pretty simple to take care of, minus, again, I could pull the 2 out in the front. That's probably nice. Then I can write it as 2, 1 over x dx minus 2, 1 over x minus 1 dx. And then I'm going to break this integral, the 2x plus 4 over x squared plus 4, into two separate integrals, two separate fractions. So I would have plus 2 x over x squared plus 4 dx, and then plus 4 1 over x squared plus 4 dx. I'm going to call them number 1, 2, 3, 4. There's 4 integrals, so I'm just trying to show you that there's 4 integrals. The 1, 2, and 4 are pretty straightforward, but number 3 is the one where I need to do u substitution. So we have x over x squared plus 4 dx. So I'm going to let x squared plus 4 be the u. 2x dx will be du. So this turns 1/2 du over u, which is 1/2 natural log of u. Okay, and the u is x squared plus 4. All right, so let's go ahead and evaluate these integrals. So it's going to turn out to be 2 natural log of x minus 2 natural log of x minus 1 plus 2 times 1/2, 2 times 1/2 natural log of x squared plus 4. And the very last one is tangent inverse x. 1 over x squared plus 4 would be tangent inverse x over 2. Again, you can do the u substitution in there. In number 4, we can do the u substitution and see this is what we would be left with, 4 tangent inverse x over 2. And we can cancel this 2 and 2. This is not necessary. Get rid of it. Okay, I think I covered pretty much all the different types of partial fractions examples. I'm going to be repeating more examples. You can stop the video here, try the next few problems by yourself, and come back and match and check with me. Okay. Actually, this one I may not have covered yet, where we have repeated repeated quadratic factors. So you have quadratic factors and they're repeated. So let's go ahead and think about breaking the partial fractions first. Okay, first we're gonna only focus on the partial fractions. I'm not gonna bother about the integral yet, and then we will come back and care for the integral x squared plus 2 to the second power. So ax plus b, because we have a quadratic factor, plus cx plus d because it's repeating. Okay, ax plus b plus cx plus d. Now go ahead and multiply both sides with the denominator, which is x squared plus 2 to the second power. I am left with 8x cubed plus 13x. Maybe I'm just going to do it on a side here. 8x cubed plus 13x equal to ax plus b times x squared plus 2 plus cx plus d, because the denominators will cancel with that. Okay, so what we would do now is we are going to distribute and combine all the like terms. So it turns out to be ax to the third plus 2ax plus bx squared plus 2b plus cx plus a d. Okay, let's combine all the coefficients for x to the third. Looks like it's only a next to the x to the third, and looks like there's only bx squared. But with the x, we have several terms. We have 2a plus c next to x, and then we have 2b plus d. 2b plus d. Okay, so we have 8x to the third is equal to ax to the third. 8 is equal to a. If I compare the coefficients, so I'm comparing the coefficients now. Compare the coefficients. So coefficients of x cubed on left hand side and coefficients of x cubed on right hand side have to be equal. So 8 turns out to be a, and b will be 0 because there's no terms with the x squared on the left hand side. 2a plus c has to equal 13, so 16 plus c has to equal 13. C turns out to be -3. Also 2b plus d has to equal 0 because there's no constant term on the left hand side, which gives me d is equal to 0 because we already found b is 0. Good, so that's d equal to 0. All right, so now we will plug these back into the equation here. Plug the a as 8x. Plug the partial fractions back in here, the value of a, b, c, d, and plug the partial fractions back in the integral. Okay, so we'll have 8x, and b is 0, so that doesn't really matter. X squared plus 2 plus c is -3, so I'm going to pull that out in the front. -3x over x squared plus 2 to the second power dx. Okay, so break it into pieces. 8x over x squared plus 2 dx minus 3x over x squared plus 2 to the second power dx. Okay, let's call this integral 1, integral 2, and I'm going to do them separately and plug back into our answer. The first one, so integral 1 is, I can pull the 8 out, and I have x over x squared plus 2 dx. And we can let x squared plus 2 be the u. 2x dx will be du. X dx will be 1/2 du. Okay. Good. So we have 8 times 1/2 du over u, which turns out to be 8. 8 times half is 4, which turns out to be 4 natural log of u, and that is 4 natural log of x squared plus 2. So that's the first integral. We'll take care of c at the end. The second piece of my integral is 3x over x squared plus 2 to the second power dx. Again, I'm going to let x squared plus 2 be the u. X squared plus 2 be the u. I did not mean to touch the eraser. Let x squared plus 2 be the u. 2x dx be du. X dx be 1/2 du. So this integral turns out to be u to the negative 2 du, which will be negative 2 plus 1 is negative 1, and then you divide with the negative, which comes out in the front of 3/2. So it's negative 3/2 x squared plus 2 to the power negative 1. All right, now let's go back to our integral that we wanted to evaluate. So I'll clean up a little here and plug these back where they belong. So the first integral, we just found out that this first one is equal to 4 natural log of x squared plus 2. And the second integral turns out to be negative 3/2 and then x squared plus 2 in the denominator plus a c. Looks like that would be it, and that's what our integral evaluates to or simplifies to. Okay, let's check out a couple more examples. Again, you can stop and try these problems on your own. Pause, try, and then come back and check. How would you evaluate this integral? Think about these three problems. Do you need the partial fractions to evaluate each of these? Can you factor the denominator? Can you think of two numbers, they multiply to give you negative 4 and they add up to give you 3, positive 3? So 4 and negative 1. We can factor the denominator. It's factorable, but I think even u substitution is going to work over here. So if I let x cubed plus 3x minus 4, so you would have to think about, for some of the integral problems, more than one technique would work. You would have to think about which one is the easiest for that problem. So we can say x squared plus 1 dx will be 1/3 du in this case. X squared plus 1 dx will be 1/3 du. Okay. X squared plus 1 dx would be 1/3 du. And then from there, you have 1/3 du over u, which is 1/3 natural log of u plus c. And that's 1/3 natural log of, let's plug u as whatever we called it in the beginning. Okay. Let's look at the next example for part 2. What are we supposed to do over here? Let's take a look for a minute. Looks like both numerator and denominator are factorable here. So x minus 2, x plus 1 dx, and the bottom would be x minus 2. You have to use rational zero theorem for the denominator, 2x plus a 2. For the bottom, it's a cubic function, and if you use rational zero theorem, all the factors would be either, if it does have any rational zeros, they will be plus minus 1, plus minus 2, plus minus 4. Okay. 1 does not work, neither does negative 1, so we check that really quick by doing a mental substitution. And if I try to divide with a 2, synthetic division, then we have 2 here, turns out to be 2 times 2 is 4, 4 minus 2 is 2, 2 times 2 is 4, and that turns out to be 0. So that's how we were able to factor the denominator. It's you could use synthetic division. It's a cubic polynomial. So now our new integral is x plus 1 over x squared plus 2x plus 2 dx. This one is an easy u substitution. Let x squared plus 2x plus 2 be the u. 2x plus 2 dx is du. We can say x plus 1 dx is 1/2 of du. And your integral turns into 1/2 du over u. 1/2 du over u, which we can easily evaluate. And the next one is 5x minus 1 over x cubed. Let's go ahead and see if I can factor it. If I factor the top, no, top is not factorable. The bottom is factorable. So I'm going to only focus on the fraction right now. From the bottom, I can pull out an x squared minus 9, 5x minus 1 over x times x plus 3, x minus 3. Looks like this would be a partial fraction decomposition problem. We would have to use partial fractions here. We have 3 distinct factors in the denominator. Let's see, what does it turn out to be? Okay, so this was equal to 5x minus 1 over x times x squared minus 9, which was 5x minus 1, x times x plus 3, and x minus 3. If I multiply both sides with x times x plus 3 times x minus 3, the left-hand side turns out to be 5x minus 1. Right-hand side is bx into x minus 3 plus cx into x plus 3. Okay, so we're going to let x be 0. If I let x be 0, I can easily find out the a by plugging x as 0 on both sides. By plugging x as 0 on both sides, a would turn out to be 1 over 9. And I can let x as positive 3 on both sides. If I let x be the positive 3, I can find out c. C is going to be 7 over 9. And if I let x be negative 3, I can find out the b, which is going to be negative 8 over 9. So go ahead and plug back in and evaluate the integrals, okay? I'm going to leave it for you to try. Plug them back in and evaluate the integrals. Okay, next few problems are really just a repetition of what we already talked about. So again, you don't need to watch the video any further. I covered all the distinct problems. For the rest of them, you should pause, try, and then check. Okay, 5x squared plus 20x plus 6 divided by, I can pull out an x squared plus 2x plus 1, which is 5x squared plus 20x plus 6 over x times x plus 1 squared. So 3 repeated linear factors. So what should I do in here? I set up my partial fractions. So I'm going to be only working with this piece now. Multiply both sides with x times x plus 1 times x plus 1 squared. It turns out to be 5x squared plus 20x plus 16. Use a little more. I'm going to go over here. Okay, 5x squared plus 20x plus 16 is a times x plus 1 squared, b x times x plus 1 plus c x. Let x be 0. Oh, my bad. This is not 16, this is 6. This is 6, not 16. Not 16. This is 6. Okay, that's a 6. So when x is 0, a turns out to be 6 is equal to a. Found the a. And let x be negative 1. If x is negative 1, I get 5 minus 20 plus 6 equal to. So negative 15 plus 6. Negative 15 plus 6 is equal to, let's see, what is negative 15? This is actually just a repeated problem that I covered earlier, so cross it out. I covered all the distinct partial fraction problems, all the different kinds of partial fraction problems already, so I'm going to stop the video here.